Today marks the episode 2 for sharing and temperature stresses, and in this episode, I'll be teaching on sharing stresses. Sharing stresses. Apart from direct stresses, in the initial videos, we talked about direct stresses, which are in tension, that's tensile stresses, and we also talked about what compressive stresses. There is another form of stress induced called the thermal stress. In the episode 1, I tackled the thermal stress. And apart from this, there is another type which we call the shear. Today I'm going to talk about the shear stress. The shear stress plays a lot of role when analyzing structures and bars. Its behavior should not be neglected when we are making analysis. So let's consider how, or let's look at how the shear stress occurs. So assuming I have a bar or this structure fixed, the structure is fixed and glued to the ground from A to B, and I decide to apply a tensile force. So this is the structure, and this is my tensile force P being applied to this member. So this member is A to B, and I am applying a force P. This force will tend to slide the surface of the bar. This is a segment of the bar. If I am to cut the bar through this line, the force is going to cause a shear to this member, and it will slide on the surface, leaving this stationary. Now we assume the bottom is glued and there's no movement in the bar, or there's no movement in AB, but a force is applied to stretch or to pull the structure. Therefore, it is going to slide on the surface, and this sliding effect is what we are referring to as the shear stress. It is going to cause what? A shear. Part of it is going to slide. So always the shear stress is tangential and parallel to the member. We can see that this force is acting what? Tangential and parallel to the bar. So the shear is going to cause at this surface. The shear stress is going to be induced at this surface. That's what we call what? The shear. So for example, if I have some coins which I group them or I put them on each other so that I get a vertical arrangement of what? Coins. Let's assume I've arranged coins in this order and they are firmly glued down such that no movement is going to occur. And I apply a force, let's say P, to this coin. There's a tendency that this coin is going to slide over the surface of this, and that sliding effect will induce what we call the shear stress. The shear stress. And shear stress is denoted by the symbol tau, and it is giving us the force over the area or the tangential area. So if I'm going to find the shear stress induced at this point of shearing, I'm not going to say the area of this bar is length times what? Maybe the breadth. No, I'm going to consider the tangential what? Area. The area of what? Sliding, where the shear is what? Induced. That's what I'm going to what? Consider. So for example, if I have a bar like this, which is going to be in a shear. Let's assume I have two bars. This bar, and they're being joined by a rivet. So a rivet, they are being glued by a rivet. So I have it this way, and I apply a tensile force P. It is going to cause an opposite force P here. So eventually this one of the bar will tend to slide over the other, and at the end I'm going to have a sliding bar, or when this force is greater than the force inside the rivet, it's going to break at this area, and this whole bar A will slide on the surface of what? Bar B. So if I want the shearing stress at the point of contact, I'm going to take this force. So that means the shear stress tau is going to be this force P over the tangential area. Now the area should be the area of contact by the rivet. The area by the rivet, not the area of the bar, because the area of sliding was at the place of the rivet. So finally when it breaks, I will get bar A in this form with this force P, and the rivet will be there and the surface. So this area of the rivet where the shearing occurred will be the area used to calculate the stress, the shear stress, not the area of the bar. It is the tangential area, the area of contact. So in this figure, I told you the area will be the surface what? Area of what? Shear. So we should take note on that. We can also apply limits when the bar is not a perfect body, and we can take an elemental area, then we apply limits and find the entire area of the bar. We will solve examples on that. And there can be a situation where the bar will be doubled. For example, this is two bars. Let's assume the bars are what? Three, A, B, C. What happens? So this in this bar, the shear stress is going to give me the force P over the area of what? Contact area. Are we good? And this force P is equal to this force P. Now, let's assume a bar. The bar is in this form. It's a triple bar. There's another bar this way. So we have bar A, B, and C, all joined by a rivet. So we have this rivet joining them together firmly. They are firmly bonded. So we have the rivets joining them together. And if I apply a force P here, it will try to slide this bar B in between A and C. And there's going to be an equal force here in the bar A. This is going to be P on 2. From equilibrium, this will be P on 2, such that this force P will be equal to P on 2 in the opposite direction plus the other force P on 2. and it's still going to give us what P to balance this bar. Let's see what happens in bar A if we want to find the shear stress. I'm going to take bar A, and this is going to happen. I'll have the bar this way, the rivet, and the force P. And this force is enough, and the force is enough, it will break the rivet, and there's going to be what sliding, and because of the sliding, the shear stress will be what induced. And if I want to use bar A to calculate for the shear stress in bar A, I'm going to consider this force. Now it's P on 2, half of the force, and the area, maybe the rivet will be what, a circular object, or yeah, a circular object. So the area will be given us pi on 4 what, d squared. I'm going to consider this area, this small area of the rivet, not the area of the bar, because the shearing occurred at the region of the rivet, meaning my shear now is going to be the force, which is P on 2 over the area, pi on 4 d squared for bar A. What of bar B, where the force P is acting? So inside the bar B, this is what's going to happen. I'm going to get a free body diagram of the bar this way, and this is the rivet. Now the rivet will be broken at two joints. Looking at bar B, the top bar A will break at A, and the C will break at C, meaning this bar B is going to have two breaking points. Are we good? Two breaking points of the rivet. This is the rivet, and there will be this force, what? P. So if I want to know the stress, which is the shear stress in bar B, so shear stress in B is going to be the force, what? P. Force P on the area. Remember now the area is 2 because one is here and the other is what? On top. 2 times the area. Are we good? 2 times what? The area, and the force is what? P, and the area can be simplified as P on 2 pi on 4 d squared. And the same thing is going to happen here. If I further deduce this formula, I'm going to have P on 2 pi on 4 d squared. So you're going to get the same answer if you consider the bar A, the bar B, or the bar C. But in bar B, you should be careful about the area because the breaking point is what? 2. The tangential stress is occurring at 2 points. This point and downward. So the area should be what? Doubled. But in bar C and A, the breaking point occurred at just a single point, and the force too is what? Half. P should be equal to the summation of the other forces for equilibrium to what? Okay, therefore, we know that shear, which is denoted by tau, is the force over the area, and mostly the force is represented by what? V, which is the force on the area. We get our shear stress. Let's solve some example on the shear stress. 3 steel plates are held together by a 16 mm diameter rivet. If the load transmitted is 5 kN, estimate the shear stress in the rivet. So you see the shear stress will occur inside the rivet or at the point where the rivet is being what? Slided. So we are going to find the shear stress in this bar. And from the diagram, we can see that the force given is 5 kilonewton, and each bar is balancing it with what 2.5 kilonewton toward cause equilibrium. So we can consider any of the bar to do our analysis. So bar A, B, and what C. So my parameters. The diameter of the rivet is 16 millimeter, which is going to give me 0.016 what meters. Are we good? And we have a force or a load to be equal to what 5 kilonewtons for the force. And if I'm to draw I'm consider bar A, the first bar. This is what I'll get. I'm going to get the bar in this form, shaded with this force 2.5 kilonewtons, and the rivet. There will be a breaking point inside the rivet, and this force is going to balance it to be 2.5 kilowatt newtons. So I have to find the area, and this rivet is assumed to be what a circular rivet. So the cross-section area will be given as pi d square on 4. So we can calculate our area as pi. Our diameter is 0.016 square on 4, giving me 2.01 10 to the power negative 4 meter square. Therefore, from bar A, my shear stress is going to be the force, which is 5 kilonewtons. Since it occurred at a single point, the shearing occurred at a single point, I'm going to use this area, single area, and the force on bar A is 2.5 kilo. So 2.5. If I'm considering bar B, then I'll use the 5 kilo. But for bar A, the force is 2.5 kilonewtons over the single area the shear occurred, which is 2.01 10 to the power negative 4. And I'm getting this as the shear is 12.43 megapascal. The same thing will happen in bar C. Let's consider the B if we are going to get the same shear. And of course, the shear should be equal. So bar B, let's see what happens. I'm having this free body diagram. This is my rivet and the bar. There's a force of 5 kilonewton, and it's going to be balanced by another 5 kilonewton. And the shear is going to, because bar A is going to slide over the surface of B at this point, there will be a shear here. And bar C is also going to slide over the surface of B at this point. And the rivet is the same with the area. The area for the rivet is pi d square on 4, and we are getting 2.01 to the power negative 4. But looking at bar B, shearing is occurring at 2 points, at the upper part and the lower part. So 2 times what? The area, because in bar A, we considered a single area, and in bar B, the area is what? Twice, because it's occurring at 1 and 2. So my shear in B is going to be the force, 5 kilonewton on 2 times the area, which is 2.01 to the power negative 4. And looking at this 2 would divide this to be what? 2.5. And at the end, you're going to get the same area or we can continue and punch this, and I'm getting 12.43 megapascal. So the only thing we have to be careful here is when we are considering the bar B for our analysis, the area, the shearing is occurring at 2 points on the bar. So we take note of that. Let's solve another example. Example 2. A punch of diameter 19 millimeter is used to punch a hole in a 6 millimeter steel plate. A force P of 116 kilonewton is required. What are the average shear stress in the plate and the average compressive stress in the punch? This is quite interesting. So let's get our parameters, or we can draw a free body diagram for this problem. So a punch of 19 millimeter is used to punch a hole in a steel plate. So we can assume this is the steel plate. This is a plate, and a punch is used to punch a hole. So a hole is being punched through this steel. So we can assume it this way. It will go through the plate to punch what? A hole. So this is the punch going through the plate. And the punch has a diameter of what? 19 millimeters. So we can have the diameter of the punch to be 19 millimeters, or 90 millimeters to be 0.019 meters. And the hole diameter, or 6 millimeter steel plate, which is the thickness of the plate. Remember, this is the plate. And the thickness of the plate is going to be 6 millimeters, which is 0.006 meters. So we have this, meaning diameter of plate 0.019, thickness of which is 0.006 meters, diameter of the punch, and thickness of the plate is given as that. So we have to find the average shear stress in the plate. What happens if the plate is shearing at the point of what? Contact. What happens? So we should know the area that would be what? Given, or the shearing area. So we can consider this small shearing area, and we can get a diagram in this form. If I'm considering, if it is drawn in what? 3D, you would see that the bar will have what? A length or a width in this direction. So we can consider the area of contact this way, where we have the thickness 6 or 0.06, where we have the length as pi what? D, because this punch is what? A circular object, because it was having a diameter, and we assume it to be what? A circular object. Therefore, the shearing surface is going to be what? The length is going to be pi d. Are we good? And we have a thickness, which is what? The height to be 6 millimeters. So in all, we are going to assume a rectangular area to be pi d as the length and 0.06 meters as the width, and together we are going to get an area. Therefore, the shearing stress tau at the point of what? Sliding will be the force over the shear area, and the force given is 116 kilonewton over the shear area. Pi D. Pi is 2217. The D 0.019 and the thickness 0.06. And in all, I'm getting a shear stress of what? 323.8 megapascal as the shear stress, the average shear stress. Now let's look at the average compressive stress or the average compressive stress in the punch. Now let's consider only the punch. The punch, we know compressive stress from chapter 1 is also given as the force over what? The area. But this inside the punch, and we know the punch to be perfect was circular object because of the diameter given. So we can calculate its area as pi on 4 d squared, perfect area, the compressive stress or compressive stress inside the punch. Very good. So we have the area of the punch given, and the force is 100 and what? 16 kilo newtons over the area, pi on 4 d 0.019. And at the end, I'm getting compressive stress inside the punch as 409.1 megapascal. Quite interesting.